Thank you to the organizers for encouraging me to come to this conference. It's really great to be here and back here in the Mini, which is very beautiful, and it's also really great seeing old friends and making new friends. So it's really nice to see this room full of people. So I'm talking about residue field domination, and this is a project which has been going on for quite a long time. Here are a bunch of different relevant references. So the work I'm mostly talking about today is work that I've been working on with Clifton Ely and Pierre Simon, and which has finally resulted in a paper which is available on the archive. And looking at Clifton is looking very skeptical of what I'm saying right now. Stop looking skeptical. Okay, so we do finally have the paper out on the archive. Hopefully it'll be appearing soon. It's part of a really very much an ongoing project, which started with the work by myself, Udi Rushovsky and Dougal McPherson, on stable domination and independence in algebraically closed valued fields. And there we were working with the idea of, okay, in our valued field, in an algebraically closed valued field, of course it's not stable, but it has this very large stable part, which comes from the algebraically closed residue field. And so in what sense do we have, does that stable part have an impact on the entire structure? So that was what we were trying to think about when we defined this notion of stable domination, which I will define in a moment, so you don't have to know what it means yet. And then sometime later, Clifton and Jana Marakova and I started thinking about the question, well, what if your field's not algebraically closed? You still have, say it's a real closed valued field, convexly valued, so you have this nice residue field which is itself real closed. What information from the residue field and the fact that it's real closed, what does that tell you about the structure as a whole? So then again, we said, well, maybe what the point was not so much, in the algebraically closed case, maybe the point was not so much the fact that you had this stable part and whether it was dominating it, but maybe it's just the residue field itself, which was nice and somehow was giving us this information and control over the entire field. And so we came up with this idea of, there it is. All right, residue field domination in real closed valued fields in a paper which appeared in the Notre Dame Journal of Formal Logic. But then when we were talking about this at some point in Berkeley, Pierre said, you know, that doesn't seem to be anything special about a real closed field. Maybe it's just the fact that it's Henselian, which is the point. And so we looked at what we were doing in the proof and said, yeah, this actually does seem to carry over to a even more general context. Although we do need to be working in some situation in which we have quantifier elimination. So we turn to the sum. That's why the title is Some Henselian Valued Fields. We need to be working in some theory of Henselian valued fields in which we have a language in which we have a suitable amount of quantifier elimination. So we were doing that, and it took a very long time for us to actually get the paper written up. And in the meantime, Mariana Vicaria also started looking at similar issues. And so by the time this has now appeared, there's also a paper by Mariana, which has a lot of stuff in common. It's not the same. She's working in a different language. She's working in some slightly different theories. And I'll say more about that as we go on. Okay, so that's kind of the setup, the context, where it's all going. But let me tell you what it's about. Oh, and I should also mention this paper of Martin Hills, Pierre, Pablo Cubides-Kovacic, and Vincent Yi, on which a lot of the kinds of arguments that we're writing down also appear, even though they're doing something quite different in that setup. Okay, so let's just go back to the very basics, to the beginning. I'm working in some valued field, which I will call uppercase K, with evaluation ring O and maximal ideal M. And this is a conference on the model theory of valued fields. I'm sure you all know everything I'm about to say in the next two slides, but I'll say it anyway, just to give us a chance to warm up and give me a chance to warm up maybe. But there is a little bit of a point that I want to make as we go through it. So I have the residue field, which I'll call lowercase k. And one should be clear, Antoine yesterday was using lowercase k for the field. I'm using it for the residue field. And of course, that's given to us by an equivalence relation. It's O mod m. And that equivalence relation is that A and B are equivalent if the valuation of A minus B is greater than 0. So that's in the, we're taking the quotient in the additive structure. And we can think of our value group as being given by an equivalence relation in the multiplicative structure of the invertible elements of K modulo the invertible elements of the valuation ring. And for an element of the valuation ring to be invertible, that means it has valuation equal to 0. And so the equivalence relation is that A is equivalent to B if the valuation of A over B is equal to 0, or the valuation of A is equal to the valuation of B. That's why it's of course, the valuation ring. I mean, the value group. And then we can put those two together by, if we take RV, which is the invertible elements of the field, modded out by the units, which are of the form 1 plus m. And so then our equivalence relation is that A times 1 plus m is equal to B times 1 plus m if and only if A over B minus 1 is in the maximal ideal, or the valuation of A minus B is strictly greater than the valuation of B. And we think of this equivalence relation as including both of the other two. It sort of fits them together in the sense that I'm looking at this valuation of A minus B being greater than something, but what is greater than depends on what the valuation of B is. So it really puts both of them together. And so indeed, we get this short exact sequence, which we have the residue field sitting inside RV, and it's sitting inside it at the level of the elements of valuation 0. So we also really need not so much RV, but the RV sub gammas, which are the fibers above each element of the value group gamma. So those elements of RV for which the valuation is equal to gamma. And then RV0 is the residue field, at least multiplicative structure. And all of these things, all of the RV sub gammas, are K internal. So this, the kind of presence of RV there is really crucial here. And it gives us these, the way I think of it always is that the residue field is the set of balls at 0, and that's also RV sub 0. And then as we go up the value group, we get these copies of the residue field at every gamma. But there are copies provided we fix an element of the field in order to map it back down to the residue field. Okay, so that's kind of our setup. We're working in this valued field, and we have these nice crucial equivalence relations. So what is this idea of stable domination? We can define it in general, although what we're really thinking about all the time, we have in the back of our mind, is an algebraically closed valued field, but we can define it in more generality. So if we take a complete theory T and some language L in which we have elimination of imaginaries, and just be working in a background monster model U, sufficiently saturated, and I'll always write capital C for some small set of parameters in U, and little a and little b will be some elements which are from somewhere in U which are not in C. And then we define the stable part as T sub C to be the multi-sorted structure whose sorts are the C-definable, stably embedded subsets of U, and we put in all the C-definable relations as predicates to make this rich structure. And what that's supposed to capture is, and we call it the stable part. It's supposed to, all the part of the structure which is actually stable. So then we'll talk about something being stably dominated if if the type is controlled by this stable part. So that is so the type of A over C is stably dominated if whenever I take some B which is sufficiently independent from A, and that sufficient independence is measured down in the stable part, which is a stable structure, so I have a reasonable notion of independence there. So if I take some B, which is independent from A in the stable part, then whatever I want to know about B over A, is I already know if I know about B over the stable part of A. Okay, so what do I have on next? Yes, okay, so.
When you write CA means ACL is A, right? Besides stable part.
Sure, so this notation means the definable closure in the stable structure, in the sort SDC of the parameters C and A. Yep, so DCL. Maybe I write it this way. I could have switched the role of A and B there, but actually let me just kind of make a point about what does this notation actually mean. I mean, what I said was I know everything about B to do with A if I know everything about B to do with the stable part of A. And this type, of course, is in the language in which I'm working. So this is all taking place in the context of this theory T in the model U, and I'm working in some language. So what does this mean exactly? All right, so it means that to say that the type is implied, this type implication notation, which we tend to write down a lot, means exactly that if B and B prime have the same type over C and the stable part of A, then they have the same type over C and all of A. And of course, that means that if I take an automorphism of the whole structure, which fixes the stable part of A and maps B to B prime, then there's going to be some other automorphism which fixes all of A and maps B to B prime. Okay, so what does that mean? Well, because the stable part of C is stably embedded, that's actually equivalent to saying if there's some automorphism which fixes the stable part of B with sigma of B equals B prime, then there's some automorphism which fixes all of A and sends B to B prime. So nobody should ask me about this because I find this really confusing and I don't have an intuition for it. But it's saying that, basically what it's saying is that if I know, I'm not going to say anything more. It's there. But also what this means, another way of saying this is that if I have quantifier elimination, then in order to get this statement about the automorphisms, then what I need is to say, if I take some isomorphism defined on the substructure generated by C and B, which fixes the stable part of B, then this extends to an isomorphism defined on the substructure generated by C and A and B, fixing C and all of A. So this is the statement that I'm actually going to be trying to prove when I'm trying to prove this type implication. And the nice thing about this statement is that in the context in which we're looking at it, it becomes a statement about fields. And so we can state it very algebraically. It's just an algebraic theorem which we need in order to get the model theoretic conclusion which we want. Right? So that's kind of rewriting it, and that in this way, it explains a lot of what I'm going to be doing as I go on. Okay, so now we know what it means for what we have to verify in order to check stable domination. Let's see what this means in the example that we had in mind in the definition, which is, of course, an algebraically closed valued field. So we'll now take T to be the theory of algebraically closed valued fields in the geometric language in which we have quantifier elimination and elimination of imaginaries. And of course, so when K is a model of T, then the field will be algebraically closed, and so also the residue field will be algebraically closed, and the value group will be divisible, and both the residue field and the value group are stably embedded. And because our residue field is algebraically closed, then of course it's stable, and so is all of the K internal structure. So we have the things which are K internal include all of the RV sub gamma and of course n-dimensional versions of them. But what we see in particular is that the stable part, STC, contains all of RV. And indeed, if our base C is itself a model, is itself algebraically closed, then the stable part C will be interdefinable with k to the n, with powers of the residue field. So what kind of examples do we get? When do we have stable domination in order to get a sense of what it looks like? So let's just, for simplicity, assume that our base C is itself an algebraically closed valued field. Just make sure that I don't make any mistakes when I don't say something wrong when I'm quoting things. So let's take little a to be a field element which is not in C, and assume that A is generic, and a generic element of the valuation ring, which means that it's in the valuation ring, but not in any smaller ball definable over C. So in particular, it's not in the maximal ideal, so its valuation is equal to 0, and its residue is not something which C knows about, so its residue is a new element of the residue field, so it's not in the residue field of C. And so that means if I take some element B, whose stable part is independent from the stable part of A, well, the stable part of A is really given to us by just taking the residue of A, and the stable part of B is given by taking the residue of B. And so to say that I have independence in the stable part essentially means that residue of B is algebraically independent from the residue of A over the residue field of C. And what that tells us is that A and B are a long way apart, and so there cannot be any interaction, any further interaction between A and B than that which we already know about because from the residue. So it will be the case that the type of B over the residue of A implies the type of B over all of A. And this is really our paradigm example of what it means to be of what it means to have a stably dominated type, as we'll see in a moment. Now, on the other hand, if I take some element of the field A, which is generic in the maximal ideal, so that means it's in the maximal ideal but not in any smaller C-definable ball, then in particular, its residue its valuation is positive, and its residue is equal to 0. So I don't get anything new from A in the stable part, but I do have this new valuation, and the valuation is something which the residue doesn't know about. So if I take some B, which is independent from A in the sense that, it's independent, so just take it, say the residue of B is equal to 0, so then I have nothing new happening in the residue field, so trivially it's independent. And and let's suppose that it has its valuation is smaller than that of A, then it's certainly the case that the type of B, I want the pointer, let's see, okay, the type of B over the residue of A does not tell us about the type of B over all of A, because in particular, this type will know that the valuation of B is less than the value of A, but that's not something that this type knows anything about. So we don't get, this is an example where we don't get stable domination. But if we allow ourselves to put the valuation of A into the base, so look for this type implication not with just C and the residue of A but in the base, but C and the value group of A in the base, then in fact I would know everything about B by knowing this. And so I have some other kind of what it looks like is what's happening is that the type of B is actually, the type of B is implied by the type of B over the residue of A and the value group of A. And this is what we want to see more of. And so we get some theorems about stable domination, which come from the book. So if I take my theory T to be that of algebraically closed, non-trivially valued fields, then we have a theorem which says that when my base C is itself a model, then the type of A over C is stably dominated if and only if the value group does not increase. So precisely, actually what I'm really saying here is that the type of A over C is stably dominated if and only if the type is orthogonal to gamma. So really, to say orthogonality to gamma, I need to say not only that the value group with C does not increase, but over any other model which is free from A in an appropriate sense. So, but the point is orthogonality to gamma. And so that's precisely what this is saying, is that our intuition that came from the example is the correct one, that the point is not to let the value group increase, and then we get stable domination. But what if we do let the value group increase? Then what happens? Well, then we get another theorem which says, first of all, suppose that our field C is maximal, so that is, it has no proper immediate extension, and then if I take some element A, and just for convenience I'll write L as the definable closure of C and A, and if what I know about that field extension is that the residue field of L is a regular extension of the residue field of C, and that the value group of L is over the value group of C is torsion free, then the type of A over C and the valuations that comes from adding A is stably dominated. So again, what we're seeing is that there are an example of putting an A which is generic in the maximal ideal is somehow in some way the general case. Okay, so let's just go back and look for a moment at the proof of this theorem and see what's this issue with this maximality. We don't actually need the full strength of maximality. It turns out that what we in fact need is a property that we've called the good separated basis property. So this is something that anyone dealing with valued fields always comes across. It's the kind of thing that you want to be true, and the fact that it's not always true is very often your issue. But it's property that maximal fields have, and it's what we actually need when we're trying to prove theorem 2. So the property says that if I take my field L as an extension of the valued field C, then it has the good separated basis property if for any finite dimensional subspace of L as a vector space over C, I can find a basis so that if I take anything in the vector space generated by L over C and try to find its valuation, then the valuation of the sum is given by the minimum of the valuation of the summands. And that means that we don't get any unexpected behavior, we don't get the valuation jumping up, it just stays at that minimum value. And that's what we call the basis being separated. And then furthermore, if furthermore we know that the valuations of these basis elements are either all either equal or their difference takes us out of the value group of C, then that's what is said to be good. And then if C is maximal, then in fact it does have, then any L will have the good separated basis property over C. So what do we need to prove in order to get this stable domination that I claimed in the lemma? What we need is this key lemma, and remember what I said about proving a type implication means what we have to show is that if I take any isomorphism of the which fixes the base elements, then I can extend that to an isomorphism fixing the more structure. So that's precisely what we have here. So the statement says if I have L and M are valued fields, C is a subset of L intersect M. If I have some kind of independence between L and M, which in this case is given by that the value groups are disjoint over the value group of C, and that the residue fields are linearly disjoint over the residue field of C, and that either L or M has the good separated basis property, then if I take any isomorphism from L to L prime, a valued field isomorphism, which is the identity which fixes C, the residue field of L, and the value group of L, then sigma extends by the identity on M to a valued field isomorphism from the field generated by L and M to the field generated by L prime and M. And so in particular, we'll get the type implication theorem that we need in order to have our stable domination statement. So proving this is pretty straightforward. The fact that you just have to write down the obvious definition of, the only possible definition of sigma on the compositum field, and the fact that that is a field isomorphism is just a straightforward argument using these hypotheses on the value group and the residue field. And then you need to see that sigma actually preserves the valuation, and for that we use the good separated basis property. So this is our kind of key lemma, which allows us to extend isomorphisms in this situation. Okay, so that's what happens in the algebraically closed field case, which was the paradigm example that we were thinking about. Now let's move to Henselian fields and do something just to see what happens in the Henselian case. Okay, so because of course, okay, a value field is Henselian if the valuation extends uniquely to any algebraic extension. And in the general Henselian field, we no longer have control over the residue field. We no longer expect the residue field to be algebraically closed. And so this stable part may in fact be trivial. But still, if we look back at that example of the generic element of the valuation ring, we didn't really use the fact that the residue field was algebraically closed in order to get a sense that the residue of that element actually determined the type over the, if I took the type, the type of some element B, which is independent from the residue of A, I wasn't really using the fact that I was working in an algebraically closed field in order to see that the type over the residue of A determined the type over all of A. So it seems like there should still be some notion of domination by the residue field, and so we try that. So this is like let's try to find something to replace this stable with this jumping to the stable part, and think what should it be instead. So in the earlier paper with Clifton Ely and Jana Marakova, we looked at a field, our theory, which is the theory of a real closed convexly valued field, and proposed the idea of residue field domination there. And now what I'm going to tell you about is a generalization of those results, where we look at a more general Henselian field. Of course, a real closed value field is an example of a Henselian valued field. And we say, okay, well, what happens with this idea of residue field domination in this situation? So from now on, I'm going to take now my theory that I'm working in T to be a Henselian valued field of characteristic 0, 0. And I'm making this kind of technical assumption. The sets of nth powers in RV are of bounded index. Now, as we observed earlier, in order to lift an algebraic statement about extending isomorphisms in order to get the type implication that we want, what we need to have is quantifier elimination. So we need to be working in a theory and in the appropriate language in which we have quantifier elimination. So when we first started working on this, we were using a theorem of Chernikov and Simon, in which they proved that in this context, a Henselian valued field, which the characteristic 0, 0, and the sets of nth powers in RV are of bounded index, then you have, and you write down your language carefully, then you get quantifier elimination. In the intervening years, they improved that theorem, so they got rid of this hypothesis about the sets of nth powers being of bounded index. And in Mariana's work, she's using that improved version of the theorem so that she doesn't have to make that assumption. And you would think that we could just also take away that assumption here, but we actually use that in a different place. We use this assumption about these bounded index also in a different place. So we weren't able to quite just put it away.
What do you mean the set of nth power are of bounded index? What exactly do you mean?
Okay, so I guess I don't mean a set, I mean a group. Right, yeah.
And bounded uniformly in N? What do you mean bounded?
I mean for any N, the collection is finite, yeah. Yeah, so Mariana works in a different language in which, so she doesn't, like there's a little bit of a very small point where in a very precise way we need to have we need to have that finiteness in order to write something down. So when we talk about the type, then we're actually, because we're working in a different language, we're looking at a different collection of formulae. So to see how our results compare with Mariana's is not completely obvious, although there's obviously a lot of overlap. Okay, so given that context, then I'm going to say that the type of A over C is residue field dominated if, when I take some B which is sufficiently free from A, I get the type implication, that is that the type of B over the residue field of C and A implies the type of B over all of A. And the taking B sufficiently free, well, again, as we did in the stable domination case, we said what we have to look at is that the stable parts are independent. So here what I'm looking at is the residue field. And I want to say that the residue field of B is independent from the residue field of A. And because I'm taking this down to a field, which is the residue field, I just have the algebraic independence in the field, so I can work with that. So that's what we use for our notion of independence here. Okay, so how does this compare? Yes? Yep.
So don't we need to adjust for the value group?
In my definition? No, so what I'm saying is, yeah, so if C actually, if my set of parameters C contains elements of the value group, I'm still just taking the residue field. So this notation means the definable closure of C and A in the residue field sort. So if I throw in some value group elements, that's not actually going to have any effect, right? Because they don't appear. Yeah. So this is a good question. What does this independence mean? This is a pretty weak form of independence to give us this implication. So it's a pretty strong property, this residue field domination. And one might say, oh, maybe it never holds at all, and maybe it's just too strong. Maybe it's not the right thing. So we'll see as we go through a little bit what happens with that. So how does it compare? If my field K is actually algebraically closed, then residue field domination implies stable domination. Okay, so let's see, how does that go? I want to get stable domination, so let's suppose I have some B for which the stable parts of B is independent from the stable part of A. Then because my field's algebraically closed, the residue field is contained in the stable part, and so in particular I get that the residue field of A is independent from the residue field of B over the stable part of C, and actually that also gives us independence over the residue field of C because of the K internality. And so because I assumed that I had residue field domination, then I get that the type of B over the residue field of A implies the type of B over all of A. And then because, again, the residue field is contained in the stable part, then if I put in more parameters, I still get that implication. So it's a stronger property in the case when the K is algebraically closed. Now, if K is not algebraically closed, then I don't, in general, get stable domination because there might not be anything in the stable part. So just doesn't make sense to ask for it. But we don't, in general, get stable domination implying residue field domination. And here's an example, which is basically the same example again. If I just keep things simple, just take C to be trivially valued, and take some element with a new valuation, so some new element, then if I take the definable closure of C with that new element, then my residue field hasn't changed. So in particular, it's a regular extension. and my value group is just generated by this new valuation element that I put in, so that's a torsion-free extension. So by my theorem, I see that the type of A over C and the value group of A is stably dominated. But this type is not residue field dominated, because we could actually take B equals A in the definition of residue field domination. And here's this point about the residue field. If I've increased the value group, but that doesn't do anything to the residue field, so the residue field hasn't gone up, and so the independence condition holds trivially, but I certainly don't expect that the type of, and here's just to see what exactly has to go into the base, I'm trying to look at the type of A over the value group of C and A. So that's my parameters are the set C and gamma of CA. So then in my definition of residue field domination, I have to look at the type of A over the parameters and the residue field of the parameters. But the residue of the field of the parameters is just the old residue field, and that's certainly not going to be enough to tell me about A over all of A. So this residue field domination is definitely different from the stable domination, but still kind of linked and conceptually. So what can we say? Does residue field domination hold ever? Well, in the context, in this setup, we get a theorem which looks very much like the previous one. So if I take again, working in a Henselian value field of characteristic 0, 0 with this condition on the sets of the subgroups of nth powers, then to add a new element and assume that that gives me a regular extension at the level of the residue field, that the value group has not changed, and that we have the good separated basis property, then the type will be residue field dominated. So we do get the kind of result that we'd like to see, with this restriction on what happens in the value group. I can't let my value group grow. I have to keep that really under control. And how do we prove this? Well, it's the same key lemma that we had before. It's about extending the isomorphisms, except now because my type that I'm looking at is in this different language, where in particular I have the RV structure there. Then when I talk about an isomorphism, it's not just an isomorphism of the valued field, it's an isomorphism of the RV structure. And so we need to make sure that the isomorphism also preserves the RV structure. And to do this is precisely where we're using the fact that we get this finite index, is to look at the formula which says which coset of RV, of some nth power in RV are you in, and that's the one that we have to look at more carefully. Okay, but then what happens if we increase the value group? All right, because we would like to do that as well. So now let's take some element for which we get a nice extension at the level of the value group, but of the nice extension at the level of the residue field, but for which we do increase the value group in a reasonable way, in an independent way. Assume we have the good separated basis property over C. Then what do we get? We get that the type is RV dominated. Okay, so what's RV dominated? All right, the point is that it's not enough just to go to the residue field. I've put in these new value group elements, and so I need to know about the residue field, not just the residue field itself, but all those copies of the residue field at all the levels of RV. And so we need to have access to those, and that's what this idea of RV dominated gets at. So we define it in this. We have to be a little bit careful with this definition. It has to be, in order to even make the definition make sense, it has to be in the setup that we're working in there. So that is that I have an extension for which at the level of the residue field, it's a regular extension, and at the level of the value group, it's torsion-free. Then we say that the type is RV dominated if, when I look at the types, I look at some M which is sufficiently free, then the RV, the fibers above above the value group of L of the RV of L, the RV parts of L, tell me everything about the type of M over L. And what's sufficiently free here? Well, this has to be, if I look at some M which contains the value group of L, then the RV part of L, as we gamma ranges over the value group of L, is algebraically independent from RV of M as gamma ranges over the value group of L. And what is algebraically independent? So we have to decide what this should mean. So we give a definition which feels a little bit contrived because it's set up to be the definition which works in order to make our argument work. But I think it's a little bit less contrived than it looks at first sight. And again, looking at Mariana's result, Mariana expresses this in a different way. Mariana expresses this by saying, if you look at think of your Henselian field as being embedded in an algebraically closed valued field, and then look at your elements, look at their type in that algebraically closed valued field, you get independence there. And it turns out that is, I don't see Mariana right now, but if there, okay, good. That certainly implies this condition, and it might in fact be equivalent. So what is this condition here? We say, if we look at elements of L on the one side, it's A's and B's, and elements of M, E, which are elements of M on the other side, and choose them in such a way that if I take the valuations of the A's, I get a Q basis for the value group of L over the value group of C. Choose the E's so that they have the same valuation as the A's, so I can quotient out by them and then take the residue. So those are some elements. And then I take the B's so that their residues give me a basis for the residue field of L over the residue field of C. And suppose that then, whenever I do that, all of those residues are algebraically independent. That's my algebraic independence. And then, with that setup, with that assumption, then what we have to do is to revise our key lemma again, which is we're extending isomorphisms. So if it's a long statement, but really it's just the same, in this situation, residue field of regular extension, the value group extension is torsion free. If I go up to some M for which contains the value group of the smallest structure, of the other structure, sorry, not the smaller one, assume I have the algebraic independence. If I have some isomorphism which fixes C and all the RV sub gammas of M, then I can extend it to, by the identity to an isomorphism to the entire structure generated by L and M, and this therefore gives me the type implication statement that I want in order to get the RV domination. And here, right here is the construction. We have such a statement for the field structure if the value group of L is equal to the value group of C. And so what we have to do in order to prove this, and this is the same argument that's used in all of these different sources, is to, we take our valuation and we perturb it to get a new valuation. And in that new valuation, we will have the hypothesis that the value group of the larger one is the same as the value group of the smaller one. And so we can apply the theorem or the lemma which worked and extend our isomorphism to get an isomorphism, a valued field isomorphism of that new valuation. And the way we construct that valuation, the valuation is our new field with this new valuation. What's the old field? New valuation. We no longer have any of the hypotheses. In this case, we don't know that it's Henselian. In the real closed case, we don't know that it's real closed. That doesn't matter. Well, all we're doing is getting an isomorphism of the field structure, or the valued field structure. And then but the way we construct that new valuation, an isomorphism of the new valued field structure is also an isomorphism of the old valued field structure, and so we get the isomorphism that we need. And the construction of that perturbation uses exactly those hypotheses that were written down for being the algebraic independence. And so that gives us what we want. And that takes me to the end, except that, okay, so going forward, what's next? We need to sort out just exactly how these two sets of results compare so that we kind of know where we are with them. What else can we do? We could look at a valued field with a derivation, behaving in what way? Valued field with an automorphism. This one, at least if the automorphism, okay, anyway, we're looking at that one. Add analytic structure. This is something which really interests me, but which is feeling really hard. We thought we had it in the real closed valued field case for a while, but it just didn't seem to work. So we're going to keep pushing on that one. What if we look at the space of RV-dominated types in a Henselian field? What is that? Do we know anything about it? Can we prove anything? Is it interesting? What about looking at an analog of the metastable groups? So instead of having a group which contains a type which is stably dominated, suppose it were RV dominated. And my student Deirdre Haskell is looking at this in the case of the real closed fields, and we'll see what happens there. Okay, that's all.